Hello everybody, welcome back. Welcome to AS online platform. In the previous class, we have started our discussion on the fault analysis for SSC JE and RRB JE students. Clear? Now, in that class, we have started the fault analysis. In that, we have seen what are the types of the faults, right? Open circuit faults and short circuit faults. And what are the types of short circuit faults and what are the types of open circuit faults we have seen there. One conductor open fault, two conductor open fault, LG fault, LL fault, LLG fault in short circuit faults, and symmetrical faults, triple L and triple LG faults. And from there we have seen LG fault is the least severe fault and triple L or symmetrical faults are the most severe faults we have seen. Later on we have seen the consequence of the short circuit faults. In consequences we have seen under voltage, over voltage, low power factor, unbalanced operation, low frequency and high frequency operation both we can get, and unstable operation. So these are the things we got in that discussion. Clear? Now coming to in this class, so here we are going to discuss about what are the objectives of the fault analysis. See here students, we are studying the fault analysis to protect the system. So we have to give the protective equipment. That means we have to design the protective equipment from the faults. See here, whenever you are seeing the fault analysis, so by studying this fault analysis, we are going to design the protective system. Design the protective system. Design the protective system. The protective system design is nothing but designing of relay and designing of the circuit breaker. So both you have to design by studying the fault analysis of the system. Now coming to the relay, what you have to design for the relay? So for that relay, we are going to select the current setting for the relay that we are going to see in the fault analysis. That is the first major objective. And coming to the second one, selection of the circuit breaker rating we have to see. Selection of the circuit breaker rating we have to see. So these are the two major objectives of the fault analysis. Sir, which current we have to give for the relay? We know relay is a fault sensing device. That's only. It is not going to trip the circuit. It is going to give the trip signal to the circuit breaker, and the circuit breaker then only it can operate and it can open circuit the transmission line. Which means that the circuit breaker itself is not going to identify the fault, and the relay is not going to itself is open circuit the fault. So both we have to study. So relay gives the trip signal to the circuit breaker and circuit breaker trip the circuit. These are the two things what we are having, students. Now coming to the relay selection. Suppose whenever you are having a transmission system like this, suppose if this is the generator which is feeding power to a transmission line. At the end of this one we are having the load. Now this transmission line is having an impedance of J1.0 per unit, J1.0 per unit of impedance in the line. Now, the pre-fault voltage at all the locations, it will be 1 per unit, for example. So, the pre-fault voltage, V pre-fault is equivalent to 1 per unit. Now, we will take two different situations or two different locations of the transmission line. We'll compare the fault currents at that particular locations. For example, once we got a fault here, this is the location 1, and once we got the fault here, this is the location 2. So up to this location, from generator to this location, so we are having an impedance of 1.0, and up to this location, the impedance will be J0.1, suppose. That is the impedance up to this location. Now, at this location, if you calculate the fault current IF1, the first situation, where IF1 is equivalent to the pre-fault voltage divided by the impedance up to that location. Up to that location, the impedance will be J1.0, magnitude will be 1.0. So it will be 1.0 divided by 1.0. So it will be 1 per unit. It will be 1 per unit. That means whenever the fault occurs at this location, the fault current that you are going to see is 1 per unit. And whereas at this location, whenever the fault occurs, so if you calculate the fault current in the second situation, IF2 is equal to, it will be the pre-fault voltage divided by the impedance up to that location will be 0.1 is the magnitude. So where pre-fault voltage is 1 per unit divided by 0.1, so it will be 10 per unit. 10 per unit. So that any one of these two currents we can select. Suppose if these two are the only situations we are having. So any one of these two situations we have to give the relay current setting. Relay current setting. Relay current setting is nothing but set current of the relay or pickup current of the relay. The current at which the relay has to give the trip signal to the circuit breaker, that is the current setting of the relay. Now see. Relay current setting. Relay current setting is also called as pickup current of the relay. Pickup current of relay. So we can denote with I pickup or set current of the relay. Set current of the relay. Sometimes we can call it as I set. That is the set current of the relay. Now, the current at which, this is the current at which the relay is going to give the trip signal to the circuit breaker. That means whenever this current occurs in the transmission line, then the relay is going to identify there is a fault on the system. Clear? So that this current is nothing but it is the current at which the relay gives the trip signal to the circuit breaker. So it is the current at which the relay operates and gives the trip signal to the circuit breaker. So this is the first situation. Now, see here, we are having two different situations. So at one situation we are having 10 per unit and one situation if you are having 1 per unit. Suppose for example students, if you are setting the relay pickup current for 10 per unit, then whenever 10 per unit occurs, then only the relay will operate. But which means that the relay will not operate for 9 per unit, 8 per unit and 7 per unit. All these things it will not operate. But whereas the pre-fault voltage in the system is only 1 per unit, and based on that one only, we are going to calculate the fault current in the system. Clear? But whenever the fault occurs at the end of the transmission line, we are having a fault current of 1 per unit. 1 per unit is also a fault current, students, that you have to understand here. 1 per unit is also a fault current here. Not only 10 per unit, 1 per unit is also a fault current, which means that before the fault, the current in the system may be less than 1 per unit. Who can say that? Why? Because we are having the load impedance also. The impedance of the system is more. Therefore, the current in the system will be less. Therefore, 1 per unit is also a fault. But whenever this fault occurs, the relay is not going to operate. Whenever if you are setting the relay current for 10 per unit. That means the relay will give the trip signal only for 10 per unit whenever the fault occurs at this location. Whenever the fault occurs at any other location, it is not going to give the trip signal to the circuit breaker. But we have to choose a relay set current it has to give the trip signal for all the faults. Wherever the fault occurs, that means what is the situation or what is the location you are getting the fault, the relay has to give the trip signal for all the faults, all the varieties of the faults also. It may be LG fault, LL fault, LLG fault, symmetrical fault, unsymmetrical fault, whatever it may be, it has to give the trip signal. Clear? Therefore, we should not choose the relay current setting at this location. We have to choose the relay current setting at this location only. Clear? At the end of the transmission line, for which current the relay is going to give the trip signal, that current we have to set as the pickup current. Clear? Therefore, this should be the minimum fault current in the system. Minimum fault current in the system. What is the minimum fault? Which means that what is the least severe fault in the system? At the end of the transmission line, the least severe fault will be the line to ground fault. Therefore, the relay current setting should be chosen for the line to ground fault. Clear? Therefore, we can say the relay current setting should be based on the line to ground fault at the end of the transmission line. At the end of the transmission line, at the end of the line or end of the transmission line, LG fault is the least severe fault. LG fault is the least severe fault. So the relay current setting I pickup should be IF minimum. So the relay current setting should be based on this current. Should be based on this current. Clear, everybody? So whenever the fault occurs at the end of the transmission line, the relay pickup current should be based on the LG fault current. Clear? Now, second one we have to see the circuit breaker rating. The rating of the circuit breaker you have to see. So if you see the rating of the circuit breaker, students, the CB rating, circuit breaker rating. The circuit breaker rating should be, always we have to give the three-phase apparent power rating. So that should be 3 times of the phase voltage into the current. This phase voltage should be the rated voltage of the system. So this is the rated voltage of the system. And I to be interrupted, the current to be interrupted. So how much amount of current that it has going to interrupt, that is the rating. So that normally this will be in kilovolts and this will be in kiloamperes. So that the rating of this circuit breaker will be in megavolt ampere. Clear? Sometimes the same rating they will give it as in line quantities. So it will be √3 times of V line rated and I line to be interrupted. So again, so this will be in kilovolts and this will be in kiloamperes, so that the rating should be in MVA. So these are the two things that you have to concentrate here, students. Right? Now, for example, whenever you are having a generator like this, and this is the transmission line connected to that one, and here we are having one more machine. It may be generator or motor, whatever it may be. We are having two synchronous machines. So which are the sources of the currents. So generator and motor also the source of current. The synchronous motor is also a source of the fault current, not only the synchronous generator. But induction machine or induction motor, we cannot consider that as a source of fault current. But synchronous generator and synchronous motor, both we can consider as the sources of the fault current. Now, whenever the fault occurs at exactly the midpoint of the transmission line, exactly the midpoint of the transmission line, see here, so this is the fault location. This is the fault location. So that the current starts flowing in this direction, IF1, and the current starts flowing in this direction also, IF2. So both the currents are moving in this direction. Both the currents are moving in this direction. And you are having the circuit breaker in this location. Suppose that is the location of the circuit breaker. Now, which current the circuit breaker is going to take here? Interrupt. It is going to interrupt the fault current to 1. Fault current 1. Therefore, the current to be interrupted, it should be IF1. Right? So, I to be interrupted is IF1. So why? Because IF1 and IF2 are both are same only. Why? Because the fault is at exactly midpoint of the line. So both currents are same only, right? IF1 is exactly equivalent to IF2. Suppose if you are having this element in this side, suppose this is the location of the circuit breaker. Now, so I to be interrupted should be IF2, right? IF1 is equivalent to IF2. Both are same only. Got the point here? Now suppose the fault is not occurring at this location. If the fault occurred at this location somewhere. For example, this is the transmission line. Suppose the fault occurred here. Clear? Now we are having the circuit breaker here. Now the current flowing here, it is IF1, and the current flowing here, it is IF2. Now which current it has to take? See here, the current which is flowing into the fault, it is the sum of both the currents, IF1 plus IF2. But the circuit breaker will see only one current. It may be IF1 current or IF2 current. Both are fault currents only, na? Both are fault currents only. Suppose if IF1 is more, the circuit breaker has to operate for that one. If IF2 is more, the circuit breaker has to operate for that one. Therefore, so here the I to be interrupted should be maximum of IF1, IF2. So whereas in previous case both are same only. So for which is the maximum current? So for that current, that we have to choose the circuit breaker rating. Now tell me, which is the maximum current possible? For which fault the maximum current will be possible? It will be for the triple line fault or triple line to ground fault. The symmetrical fault currents are the most severe faults, so that the circuit breaker current rating should be based on the symmetrical current ratings, symmetrical fault current ratings. Clear? So that at the end of the transmission line, transmission line, three-phase faults are more severe. So, the circuit breaker rating should be based on symmetrical fault currents. are three-phase fault currents. Symmetrical fault currents are three-phase fault currents. Three-phase fault currents. Clear? So based on this only, we are going to design the circuit breaker as well as the relay. Clear? We got some questions on this one also. In the previous year exams, we got some questions on circuit breaker rating as well as the relay rating. Clear? Now we'll see students here. So first of all, we are going to discuss about the line to ground fault analysis in the system. So what is line to ground fault? And for that one, what are the derivations we are having, what are the formulas we are having, all those things we have to see here. So here we'll consider a three-phase generator. This is the three-phase generator whatever we are having, and assume that it is operating under no load condition, right? So here we'll consider a three-phase alternator operating under no load condition. Clear? And it is grounded through an impedance of Zn. This is the grounding impedance. Right. Now we are told that it is operating under no load condition. That means before the fault condition, the current flowing in phase A is 0, and phase B is 0, and phase C is also 0. So all the three currents are 0 before the fault condition. Here IA is 0, and IB is 0, and IC is also 0. IA 0, IB 0, and IC is also 0 before the fault condition. Clear? And the generator, the induced EMF of the generator in phase A is EA, EB and EC. They are balanced, right? We can say if EA is having a magnitude of E, it is having a magnitude of E at an angle of 0, then EB will be having magnitude of E at an angle of minus 120, and EC will be having magnitude of E at an angle of plus 120. So we are saying that these EMFs are balanced in nature. So they are having equal magnitudes and having a phase angle difference of 120 between them. Right? Now on this system, we got a fault. So what is that fault? We are saying that it is a line to ground fault on the system. So that between phase A and ground, we got a fault. That is the line to ground fault. So initially we can consider that fault as the bolted fault. Bolted fault in the sense it is dead short circuit fault has been occurred between line to ground. And based on that we can start our analysis. Clear? So that we'll assume a bolted in the sense dead short circuit fault. Dead short circuit fault. Dead short circuit fault in the sense there is no fault impedance. So between line and ground, there is no impedance existed here, right? So that it is having zero impedance path. Dead circuit fault has been occurred between phase A and ground. Between phase A and ground. That is the initial situation we can take, right? So that we got a fault here. This is the fault. Now, so that the fault current is flowing here, this is the fault current we are having. Clear? So that this A phase is having a current to the ground, right? Therefore, that A phase current is not is equivalent to 0. So initially A phase current is 0 under no load condition. Now it will be not is equivalent to 0. So that based on this one, we have to write some conditions here. So what are the conditions that we can write? Right? So I will write, first of all, what are the pre-fault conditions. Later on, we will write these post-fault conditions. I will see how to write. Right? So just I will show you so how to write those conditions. So first of all, the pre-fault conditions. Pre-fault conditions. Before the fault occurrence in the system, what are the types of the fault, what are the equations that you are having? Just check here. Before the fault in the system, we are having IA is equal to 0, IB is equivalent to 0, and IC is equivalent to 0. So all the three currents IA, IB, IC are 0 before the fault in the system. And the neutral current IN is equivalent to IA plus IB plus IC. Just check it. So neutral current IN is the entering current. IA, IB, IC are the leaving currents. So as IA 0, IB 0 and IC 0, we are having IN is also equal to 0. So that the value of IN is also 0. Clear? Right. And as the initial system is under no load condition, the terminal voltages are exactly equivalent to the induced voltages. What are the terminal voltages we are having? VA is the terminal voltage, VB is the terminal voltage, VC is also the terminal voltage. Therefore, VA is equivalent to EA, VB is equivalent to EB, and VC is equivalent to EC. Right? Therefore, we are having the induced voltage and the terminal voltage are exactly same. VA is equivalent to EA, VB is equivalent to EB, and VC is equivalent to EC. What is EA, students? Magnitude of E at an angle of 0, and it will be magnitude of E at an angle of minus 120, and it will be magnitude of E at an angle of plus 120. Clear? So that all are having equal magnitudes with 120 degrees phase difference, so that we can say this system is a balanced system. So that initially the system is operating under balanced condition. So this is the balanced system. Clear? So which means that the initial system is operating under no load condition. So because of the no load condition, we are having the balanced system operation. Clear? And this is the pre-fault condition. And if you see the post-fault condition, the post-fault conditions of the system. The post-fault conditions. So after the occurrence of the fault, the post-fault conditions. Please check here, students. Once the fault occurs, whenever the fault occurs in the system, the A phase current will become unequal 0, is not equivalent to 0, and the fault current and A phase current are same. Therefore, we can write the fault current and A phase current are same. IF is equivalent to IA, and there is no change in the remaining currents. What are the remaining currents? B phase current is 0, C phase current is also 0. Therefore, IB is equivalent to 0 and IC is also equivalent to 0. So these are the two currents we are having as 0. And coming to the next one, the voltage condition, if you check here, that A phase voltage has been grounded. When A phase voltage has been grounded, that means that A phase voltage will become 0. So why? Because the ground potential is at 0 volts. Therefore, so this point and this point are at the same potential. Therefore, VA will become 0. Therefore, this will be VA is equivalent to 0. So these are the post-fault conditions that I have written here. See here? These are the post-fault conditions from this circuit what we can write. And by using these conditions, we are going to calculate the sequence currents, sequence voltages and sequence network of LG fault and all the required derivations we are going to see. Clear? So first of all, we'll see the sequence current conditions. The sequence current conditions for the LG fault at A phase. At phase A, we'll see. At phase A. First of all, just check here, students. Sequence current conditions. Sequence current conditions. Sequence current conditions of phase A. Phase A. What are the sequence current conditions of phase A? If you see here, we are having the sequence currents IA0, IA1, IA2 is equivalent to 1 by 3 times of 1 k square and 1 k square k into IA, IB, IC. So all these things we'll see in chapter 2. So in chapter 2 of the fault analysis, what we are having there? Symmetrical network representation or symmetrical components. So in symmetrical components, so how to represent all these things in terms of K? What is operator K? Operator K is nothing but so shifting of a vector anti-clockwise by 120 degrees. So we know the value of K is nothing but 1 at an angle of 120 and K square is nothing but 1 at an angle of 240. So which is nothing but 1 at an angle of minus 120. So both are same only. Clear? So we'll see all these things in chapter 2 and the application we are going to use here. So without understanding chapter 2 and chapter 3, we cannot come to chapter 4. Clear? So in fault analysis particularly, so to derive any formula of the fault analysis, so we have to go for chapter 2 and chapter 3 and by using the per unit system also. Now check here, IA0, IA1 and IA2. And here, just we have written the formulas. After the fault condition, also IB is 0 and IC is 0 also on the system. Therefore, here IB will be 0 and IC is also 0. And from this one, we can calculate. Tell me what is IA0? Therefore, what is IA0? The value of IA0. The value of IA0. IA0 is equivalent to 1 by 3 times of 1 into IA, 1 into 0, 1 into 0. 1 by 3 times of IA. And what about IA1? 1 by 3 times of 1 into IA, k into 0, k square into 0. 1 by 3 times of IA. And what about IA2? 1 by 3 times of 1 into IA, k square into 0 and k into 0. So it is also 1 by 3 times of IA. Therefore, we can write from this, we can write that IA0, therefore IA0, the zero sequence current, the positive sequence current and the negative sequence current, all are is equivalent to IA by 3 for line to ground fault. Line to ground fault. So that we can say all the sequence currents are equal for LG fault. All the sequence currents are equal for LG faults. That is the condition of the currents. And if you check here, for single line to ground fault in conventional phases, so which are equal? All the currents are equal. All the sequence current will be equal. So the sequence current components of currents are equal. So positive and negative sequence components are equal and zero sequence currents are 0. So here it will be 0. zero sequence currents are 0. And all sequence networks will be in parallel, no. So zero sequence component only will be present. What is the correct answer? Just now we got here. What is that? Just now we got here. IA0, IA1, IA2 all are equal. So all the currents will be equal. So that the sequence components of currents are equal. We can say here it will be IA0 is equivalent to IA1 is equivalent to IA2. So all are equal for line to ground fault. Like that we can solve, right?